Okay with me.
Yeah, okay, it's recording. So, yeah, so this is okay.
Gautam,
Yeah.
I have just one thing like the homework submission link and the homework are not yet uploaded. So I was wondering if we have to submit something this Sunday or not.
This Sunday, yeah, I think there is a homework this Sunday.
It hasn't been posted.
Yeah.
So he hasn't posted?
No, there's no submission link on CCLE, and the homework he said that he'll be adding 2 problems. I don't see those problems as well. So
Oh, then in that case, okay, I'll ask him and I mean, I don't think there is, but I'll confirm with him. Okay, so I don't. Yeah, I'll have to confirm with him. I actually thought he did upload. I didn't check it.
okay.
Yeah.
Okay.
Okay, so I'm going to try to like explain very basic things like in half an hour. So just so that everyone is on the same page. So this is what basically the transistor, the 22 nanometer transistor looks like. Okay. So you have, so this is your SOI. I mean, most of you know what SOI is now. So you have this is the silicon on insulator region. And then you have a gate on top. So let's annotate here. Yeah, so this is your gate. And then this is usually where the high K is. You have a hafnia here, or hafnia silicon oxynitride. And then this is your, basically this is the region of the SOI, which is going to conduct the current. And then you have a source drain contact. So everyone knows about LDD MOS, right? I think Subbu, a professor, had posted a paper or something. Yeah, so I hope everyone has read that paper. So basically, you have this N- region near the channel because you want to reduce the field, electric field in this PN junction, because there are some sort of high field effects that happen if you don't do that. So there's actually an N- region here, and then there's a heavily doped N+ region here, which you see here. And the contact is usually made to the N+ region because you want, you basically, it's difficult to make, if you make contact to a lightly doped region, you'll have something called a Schottky junction, which prevents your current from flowing. So you need to always contact to a material, the semiconductor that's heavily doped, so that you make something called an ohmic contact, which basically allows current to flow in either direction without any barrier. And then, so you have the source drain and you have the gate on top. What makes the SOI unique is that you also have, in the backside, right? So this is your box. This is your back buried oxide. So on the backside of the box, you have this substrate material, right? So you have this substrate and you have this well, say an N+ well over here. So what makes the SOI different from bulk MOS is that you actually can provide this back gate. So you have two gates here. So you have a front gate over here and you have a back gate here. And you can apply a back gate potential over here. And what happens is you have like, this is called as a symmetric dual gate transistor. So what it means is that you have a channel, you have a gate on top and gate on bottom, and then you can basically provide a potential for both the gates to control what the channel conductance actually is. So this is different from an older transistor, like the more commonly used transistor, where you don't have an isolation in the bottom. So you have a direct contact to the bottom rather than a capacitive contact. Yeah. So actually, yeah, so that's what the SOI transistor actually is, like how it is different from bulk MOS. So you guys have any questions here?
Is that back gate actually applied to the actual backside of the wafer, or it is etched all the way down into that?
Yeah,
into the backside.
No, it's not contacting from the backside. So the current, right? So if I was plotting the charges, so the conduction path is like this.
Okay, I was just making sure that wasn't just like some drawing thing that you were doing.
Oh no. Yeah. It's yeah. So yeah, it contacts this substrate over here.
Is that actually physically there, or is it like the buried gate that was shown in the FDSOI video, where it's not physically there, but it acts like that because of the oxide in the middle, the box in the middle?
Yeah, so you need to somehow contact this. I mean, you need to somehow excite this capacitor, right? So you have this capacitor. So the only way to do that is to contact this somehow, right? So you bring the contact to the top side because everything is connected from the top side.
Oh, okay. So the only difference here is that you moved the contact to the top instead of the
You can't have contacts in the bottom. Yeah, all contacts are in the top surface.
Okay, got it. Okay, thank you.
Yeah.
One question: is all the body is the body of all transistor connected?
Oh, you mean like shorted?
The N plus region at the bottom below box, are they all connected?
So this entire region is like is conductive.
No. Is it connected to other transistors, like the one besides it?
No. This region is only for this transistor. Of course, if you have two transistors that have the same backgate voltage, you can of course short this. So you implant it in such a way that they are shorted. But in my drawing here, right? This is an NMOS here. This is a PMOS over here. So for the PMOS, you would have actually a P plus region, and it will be connected to VDD.
Yeah. Yes. Thanks.
Yeah. Okay. So that's basically so. So in our case, right? So what we are going to do is, like I mentioned, the backgate is going to be grounded. You don't need to bother too much about this. Just when you do the Coventor simulation, right? You need to set up what the voltages for the different transistors are. I mean, for the different terminals are. So in normal operation for the NMOS, you basically set up, this is basically backgate is grounded, the source is grounded. You apply some voltage here between the gate and the source, and then you apply some voltage here between the drain with respect to the source. Okay, that's basically how you excite this transistor. And similarly, you have for the PMOS, it's slightly different. You have a different set of excitation conditions, which is there in this file. You can see I think it's towards the end, but you basically provide these excitations when you do the device simulation, so that you can basically electrically simulate your transistor. So let's see. So some things I want. So yeah. So some basic things again. I can't cover these things in like enormous detail, but then just to get a basic idea, because some of these terms you actually need to design your choose materials and so on. So the thing is, yeah.
What is FG?
FG. Oh, that's the front gate. This is FG. Front gate and back gate. Okay.
Okay. Thank you.
Yeah. So so before we talk about, so by the way, the MOSFET that we are going to use is something called partially doped. Okay. It's, partially depleted, not fully depleted. Okay. So the partially depleted MOS operated in this fashion works very similar to a normal bulk MOS. Okay. So the equations that describe the threshold voltage and all for this partially doped, partially depleted MOS is the same as a normal bulk NMOS and PMOS. Okay. So the design equations, you can refer to any standard semiconductor book for the threshold voltage and all that. So basically, let me just briefly talk about a MOS. So for example, here you see I've drawn an NMOS here. So this is a normal NMOS. Okay, so this is what normal NMOS looks like. So you have some connection to the source, the drain, the gate, and then this is basically you have the source and drain junctions. You have the substrate. And then the substrate is connected to some voltage BB, okay? So if you simplify this, what exactly this looks like is it's actually an NPN transistor. So you can see here there's an N minus, P, N minus, where the P region is actually basically connected to a metallic gate through an oxide. So it's capacitively coupled to a gate, okay? So that's what physically, I mean, a simplified model of this transistor is basically an NPN transistor with a gate on top that basically modulates and creates a channel between the source and drain region. So this is something that you guys need to probably would have seen before, but this is something that you need to design the transistor. So just some basic things like work function. So in every metal is classified by something called as the work function. The work function is basically the energy that is needed to remove an electron from the Fermi energy to, so E free is basically called as a vacuum level. So that's the energy level where the electron is freed from the solid, okay? And the Fermi level is basically the energy that sort of determines up to what energy the electron states are filled at 0 Kelvin, okay? Again, I mean, I don't know a better way to explain this because it's just like, yeah, I mean, if you guys have any questions, please do ask me. Yeah, so that's, you have similar concepts for semiconductor as well. So a semiconductor has something called a conduction band and a valence band. So that's EV and EC. And a semiconductor also has a Fermi energy EF. Where the Fermi level is located with respect to the conduction and valence band in a semiconductor determines what type of semiconductor it is. So if the Fermi energy is close to the conduction band, it's an N-type semiconductor. If the Fermi energy is rather closer to the valence band here, it's a P-type semiconductor. And you have similar definitions for semiconductor as well. The work function is again the energy needed to remove an electron from the Fermi energy to vacuum. So that's called as the work function of the semiconductor. And then you have something called electron affinity, which is basically the energy from the conduction band to the vacuum level, okay? So every material has these fundamental properties. So why these properties are important is because when you choose your different materials for your gate, right, your threshold voltage is going to depend on these different work functions as well as these different parameters. So you need to enter the correct material parameters to get how the threshold and all that, basically the threshold voltages. Hello? You guys are good, right?
Yes.
Yeah.
Oh, okay. So this is again some basics. So in any semiconductor, what happens is that the electron and hole concentration is very sensitive to where the Fermi energy actually is. It's actually an exponential dependence. Okay. So the thing is, so for example, as this Fermi energy here moves up closer to the conduction band, for example, the electron concentration in the conduction band is going to increase exponentially. And the same applies to the valence band as well. As the Fermi energy moves closer to EV, the number of holes in the valence band is going to increase exponentially. So there's this sort of exponential dependence of the carrier concentration with the actual location of the Fermi energy. So actually, I'll skip over some of these things. Like I know most of you know what a p-n junction is. So if you have a p-type material and n-type material here, and a p-type material has a lot of holes, the n-type material has a lot of electrons, and when you place them in contact, what happens is because of the concentration difference. Okay, I have just 10 minutes, so I think I'll have to continue this later on. But yeah, so the p-type has a lot of holes, the n-type has a lot of electrons, and because of the concentration difference, the holes and electrons are going to sort of migrate opposite. And at the junction, they sort of recombine, and you have something called as a depletion region that is developed there. So if you look at the energy, right? So how does the energy looks like? So here I've shown the energy diagram of a p-n junction. So in the p-type material here, you see the Fermi level is close to the valence band. In the n-type material, it is close to the conduction band. But when you go from the n-type to p-type material, you actually have this built-in potential because of this this diffusion that I mentioned here. And so because of that, the band actually starts bending, which you see here. And I mentioned earlier that when these conduction and valence bands are very sensitive to where they are with respect to the Fermi energy, right? So because the band bends here, as you get, basically when you get here, because of the exponential dependence, this region is going to be completely depleted of charge carriers. So this region where the band bends does not have any electrons or free electrons or holes, and it is called a depletion region. It's completely devoid of any free carriers, okay? So that comes to the basic transistor. So for example, so you have this transistor, you have this N, P, and then N region. So you have two p-n junctions here. So you have one p-n junction here, one p-n junction here. And if you plot the energy diagram, right? So this is the energy diagram. So you have one PN junction here, and you have one PN junction here. And if you notice, based on how I connected the voltages, right, you will find that this PN junction is always, there is no, this PN junction is not biased. So it's always has a built-in potential, which is similar to a normal PN junction. While on the right side, you will find that this PN junction is actually in reverse bias. So if you plot the energy band diagram, right, so you get like sort of a structure like this. And what this basically does is it prevents your electrons from crossing between the, across from the source to the drain, okay? To make the electrons conduct, what you need to do is you need to apply a gate potential. The gate potential actually induces a sheet of charge, like, let me, yeah, so if you apply gate potential, it actually induces a sheet of charge in this p-type region. And that sheet of charge actually begins to conduct electrons from the source to the drain side, okay? So that's how a transistor actually works, as in how it turns on and stuff like that. So actually, so since we only have 5 minutes, most of the other stuff is like how you derive the threshold voltage. I mean, this is again like device physics stuff. Which I can cover next time if you guys want me to cover, but you can just have a look at it and refer to some books. But basically, I have sort of summarized here, okay? This is what is important for the project. So I've summarized here the different equations that you need for the NMOS as well as the PMOS. So for your project, right, what we need to do is you refer to the ITRS PIDS, which tells you what is the threshold voltage the transistor has. You choose a certain material for the gate, okay? So the material for the gate is going to determine your, for example, the work function of metal. You are going to dope the semiconductor channel to a particular level that is going to determine the work function of your semiconductor. And then you choose a particular oxide thickness, oxide dielectric that determines your COX. And so basically what you do is you enter all these parameters here, and that gives you a threshold. So this is like a reverse design, okay? So you know what the threshold voltage is. You need to choose the parameters of the different, by choosing different materials, different dimensions of transistors and so on, to get that threshold using these formulas, okay? So this is a good starting point that tells you how you choose the basic design properties of your transistor. And then you fabricate it, and then you test it, and then you do some adjustments to make sure you get the correct values. So that's like an overall view of how these equations are going to be used in this project. So, you know, right, like I was just thinking, so this is what they call drinking from a hose, right? There's like a whole bunch of information here. And obviously, I don't expect you guys to, like, if for those who have not seen this before, obviously it's just not possible to follow. But unfortunately, this is more like a prerequisite for the course. So it's like something that I know professor is not going to discuss much in detail. But if you guys really want it, I can spend more time on each of these and discuss later on. But these are things that you can refer either to these, either online or learn. I have uploaded some resources where you can refer to these things, and you can ask me if you have any questions, and I can go more in detail through these things. I will go a lot in detail into the process for 22, but the physics behind the devices, I thought I would just give like a very quick thing. But if you guys want me to discuss this in detail, I can do it the next time. Okay, so I think that about concludes it. Because I don't think I can cover all this in like 30 minutes. So it's, so again, like if you guys have any question, you can always ask me.
I have one question about the SOI MOSFET. When you provide a backgate, is that the same as like substrate biasing, or it's completely different from your typical substrate biasing?
No,
in
it
a
is
MOSFET?
substrate biasing. So actually, since you asked me that, let me discuss that. So here you have a MOS gap. Okay, so this is the I'm just drawing the vertical direction in the SOI. Okay, so that's what I've drawn here. So what happens is, so say the back gate is grounded, right? And this is my front gate, and say I apply a potential. Say I apply some potential here. Okay, and what happens is this potential is going to basically So if I apply positive potential here, it's going to push the holes from here into this region, right? Because the holes are going, and so what happens is this band actually starts bending. And when this band bends, you get this region that is completely depleted of carriers. What happens is in a normal MOS, right? In a normal MOS, what will happen is you say the transistor is on when this band bending here reaches a certain value called, I don't know if you've heard of 2,5B. So
yes.
Yeah. So when the surface potential reaches 2,5B, that's when the electron concentration on the surface is the same as the hole concentration in the bulk. And that is when you say your transistor is actually on, okay? So when your surface band bending reaches that 5B. But the thing is, in a normal MOS, right, as you increase this voltage and when this voltage reaches the threshold, your band is going to be somewhere, say it bends, right? It's going to be somewhere here. So your depletion region is going to be till here. And then you're going to have some charge over here, okay? But in these SOI MOSFETs, what actually happens is, as you keep increasing this voltage, what ends up happening is, because this SOI it's much thinner, you will reach a point wherein even before reaching 2 psi B, your silicon is completely devoid of any carrier, okay? So the silicon is completely depleted over here. So you have no charge carriers here, even though you still have not reached 2 psi B. Okay, so this is what is called as a fully depleted SOI. But the one we are dealing with is called a partially depleted SOI. So what happens in a partially depleted SOI is that you don't reach all the way till the end, but your psi B is sort of, your surface potential reaches 2 phi B within that sort of SOI region, basically. Yeah. So the thing is, to answer your question, the equations remain the same as long as it's partially depleted, because when you do a partially depleted thing, you have, so this region, so you see that the potential here is still 0. You have this region depleted. And so your equation is going to be the same. But in a fully depleted case where the depletion region reaches all the way to the end, the potential diagram that you have is different, and your threshold voltage is, you need to take into account a potential drop in the oxide as well. But for partially depleted, you'd use the same equation as your bulk MOS.
I see. Yeah. I think we're out of time. So
Yeah.
thank you.
Yeah, no problem.
Thank you.
Yeah, thank you. See you.
Thank you.
Thank you. Bye.